Hello, good morning to all. In this video, we'll continue with the QSPI IP design. And in last part 3C, it was already long enough video there. So I decided to have the separate video for the simulation. So we start with the architecture here. So just for the review, what signals we have here. So you can refer the earlier videos for the same, and as seen on this slide, there are signals like clock, reset, start, busy, data receive buffer, command, address, length for TX, length for RX, then status data, then set buffer, and there are some intermediate signals are there: data send count, receive count, then send buff, then spy dual chord mode, dummy out, then address mode, and these are the DQIO and the QI. These are the bidirectional input from this CD TX-RX module. And the last is our memory model for the MX25 series. So in this we are considering device from the MX, but we can take any device, and our coding style is in such a way that you can map your referred instruction set or the command set using the command map module. And CDTX-RX is almost intact for the any devices like MX or W Winbond and the whatever the IP you are referring. So moving back to the file structure, we are taking the model, then we create a command list.vh for the defines, then TXRX module, then command map, top, and the test bench, and there are some certain data files are there. So it is already covered in the last video, but for the view, just a review, I just add this slide here. And we already know that the VCS tool tutorial has all the details regarding how we can place the files in code folder and VCS folder. Make files are there. So just for the review, we just recall code. There is a code folder where all the source files are located, and there is a VCS folder where the make file for the VCS compile and simulation is there. And there is one file list which reside on all files.txt where all the path of the source files are there. So to run the simulation on the VCS, just have the make top equals the name of the top, which is our test bench, and the mode is equal to RTL. Mode may be synthesis like. So we begin with the simulation process. So we just overlook the that test bench file for the same. I hope you already seen the all other files in earlier videos. So just we check the test bench file. So this is our test bench file where the clock is created here. This is instance of the top, and I just create one log file there, QSPI testbench log.txt, where we are storing all the signal, or we can say that the commands and the what we retrieve from the flash. So initially we place the reset here, and first command is 03, that is our normal read. You can have the earlier video where all the list of the read related commands are there. Okay, so we go in this sequence only: 03, 0B, BB, 3B, EB, 6B, E7, like that. So keep in mind this table. So we are going back to the simulation test bench. This is our first 03. Then we can have the read of the data that we received from this command. obviously there is an address is we are keeping as 100000, and we are trying to read almost 8 byte from the flash. Then fast read 0b, same, this pattern is same, we just copy paste and just change the command. Okay, so we change the read, fast read, then 0b, the rest of the things same, then bb, rest of this things are same, 3b, like that. So it is a test bench which reflect the process of this read related commands. Okay, and we are just trying to get the waveforms from this. So we just quickly moving back to this, there is a command make top equals to tb QSPI top, then mode equals to RTL. So we just enter this. Okay, so what are the signals that we are looking for? We just create that into waveform file. Create means we just drag and drop there. So we go to this UUT, then we just have this clock reset, then start. These are the addresses, lengths, and we can add all these things because it is under the top. So Control A, Control 4, it will pop up a new window for DVE. Okay, so it is a waveform window. And next most, we don't need any signals from the map. It is we can add this too. Okay, Control A, sorry, select this and hit Control 4, then we can find that signals are added here. Okay, so from the flash we can add the required signals. These are the pins, so we also need it. So there are some certain signals or registers we add. We can add these things from SPI, QPI. Then we need these things to be not in this simulation, but later on we need this, so we add these signals. Then we need what command it receive from the our driver or controller. So this command, then address and dummy, we need these registers there, and additionally we need the data also. These signals are required to debug the things. Okay, so Control 4. Okay, I hope it is added there. No, not really. So we select it. Control 4. Now I think it is added there. Okay, then from the SPI engine, that is CDTXRX, we need these are already added there. We need these signals, the dummy, mode, the receive buffer, number of bit parallel. We already have this command length, everything there, but we need a bit count. Then we need receive shift register, then byte count. Okay, and then debug TX data. Okay, this much we need. Okay, I hope these are added here. Okay, now we can able to simulate and check and verify these things. So just hit F5. Obviously there will be the creation of the log file there, but for analysis we can go by the waveforms itself. So first is this debug tx data. It reflects the what command we are sending, that is our 03, 0b, bb, 3b, 6b, e7, eb, like that. So whatever the waveforms we are seeing in between this, it means it is related to that particular command 03, 0b, and all these are related to the read command. So first, for the command 03, what we are receiving in command register 03, 0b, bb, 3b, it means we are receiving the proper what command we are sending. So we can also check the addresses what we are receiving here. So for that we have to scroll down. So obviously all the address is same for all the read commands. So we confirm that we are sending the proper commands as well as the proper address. And what more we can check. So we can check the data as well in the receive buffer. Here we can check the receive buffer. So for all the commands we are getting the data 0, 1, 2, 3, 4, sorry 1f, 5f, sorry 0, 5, 0, 6, 0, 7, 0, 8, 1, 2. So in this way we can have the check what command, what address we are sending, and particularly these signals are copied of these signals. So either you can keep this signal or we can delete from the from this, so it not look to be duplicated. So this is also the same signals we are receiving. Okay, and one more thing is that this is our busy signal. Once we have placed the commands, it will goes into busy state. So that's it. It is a start. At every process there is a start pulse, and then we place all the details like commands, address, like that. So if you are looking one of the signals, that this is our chip select. Once the process starts, chip select goes to low. We are sending the command on this SI pin, and after the command we are sending we are receiving the data from the SO pin for the 03, but it will gradually change to the SPI, then dual, then goes to the chord, then goes to the chord also, then goes to the chord also. So from this we can reflect that the whatever our command table is reflected here, SPI, then dual, then chord. So in this way we can verify the waveform and simulation. So I hope you got the point. Okay, so it is not necessary that these are the only signals you look for. You can add your own waveforms to get the things in better way, but what I'm looking for, that is a minimum signal that we have to add for the simulation purpose. So I hope you got the point, and in next video we are going for the either device related commands or write process. Okay, so might be this table get changed for the device related commands or write related commands. Okay, so thank you for watching this video, and please subscribe, like and share, comment. and support me. Thank you. Bye.